Welcome back. We are with Allen High School, and we are continuing our discussion on quantum numbers as we study the structure of an atom. Now, our second quantum number is given the letter L as its designation, and it is called the angular momentum. Hopefully you can see as the electron is continually moving around, trying to get close to that center of positive charge, that there's got to be some angular momentum or angular movement to it. Now, another name is subshell. I don't use that as much, but you may see that come up. Now, here's the key that I want you to focus on here. It's going to give us, again, about that probability region, information about the shape. Now, it also is going to give us a little teeny bit of information about energy. Now, primarily, energy is given by N, but we'll find that L contributes just a little bit to that. Now, every energy level N has at least one sublevel. Some have more, just like some homes have 1 story, some has 2, some have 3. Different energy levels have differing number of sublevels within them. So let's fill out a table and look at what we're allowed to have. We're looking at mathematically feasible, physically reasonable values for these. And we find that L can take on all integer values from 0 up to an upper limit of n minus 1. Doesn't mean that L is equal to n minus 1. It means that n minus 1 gives us the upper limit to that. Now, let's take a look here. If n is 1, then n minus 1 is 0, and that's all we get for L. In other words, n has one sublevel. So n equals 1 has one sublevel associated with it. If n equals 2, you start back again at 0. n minus 1 is 1, so now we've reached our upper limit. So we have 2 sublevels. Hopefully you're going to start seeing a pattern here. n equals 3, L starts back at 0 and 1 and then 2. And that's it, because n minus 1 is 2. That gives us our upper limit. And you notice that had 3 sublevels. And we could hop on down to here, to 6. It'd be 0, 1, 2, 3, 4, and 5 would be our possible sublevels. So 6 sublevels for n equals 6. And the designation for these is going to have some overlap associated with them, as you'll see. Now, what I'd like to do now, we're going to give this a try, is I want to show you some pictures of what these shapes look like. You have a link to those pictures. I don't think I can link directly, but I've pulled it up. Wasn't sure if I could do that, so I've got it pulled up for us. And we'll look at what these shapes are like. Now, this is called the winter. It's a winter group. I think it's just some research group, and they have orbitals online, and I love them. This is just the best website. Now, this is called the 1s orbital. Well, how did I end up with an S? I thought we were talking about L here. Well, here's the difficulty. If you had to tell me what your address was, and it was all numbers, if I had, you lived in the 42nd state, in the 38th city that was founded in the 42nd state, on the 160th street, I think you'd get the idea. It'd be very confusing. So what we do is we keep that number for n that we have there, and then we give L a letter designation as well. So what we'll find is that when L is 0, we call that an S. They're like synonyms, symbolic synonyms, you can think of them. When L is 1, we call it a P. When L is 2, it's a D. When L is 3, it's an F. And I'll give you ways to learn that in a little while. So that's the numerical. This is the symbolic. This was what you learned in pre-AP. This is your additional AP IB level understanding of these are the quantum numbers. So for this orbital, L equals 0 is a sphere, which kind of resembles a 0. So in this one, we would say L is equal to 0. You are going to have to go back and forth between those numbers and letters, so you want to be paying close attention to that. Now, this is just a cutaway of this, and if I could look at the electron density with, graphed against R and a probability region, that would show you the probability of finding R. The bigger the curve, the greater the probability of finding the electron, and we'll see some of those as well. Now, as we go to 2s, let's take a look at our 2s orbital. And let me bring that back into the middle of the screen there. Now, here's the differences. So this is 2s. Now, what's not shown on these is the size differential. And I'll see if I can help you with that a little bit. So if we say 2s, we're telling you that n is 2. We're in the second energy level. If it's s, that's our L, and it means L is equal to 0. So we want to get used to those symbols. We want to keep going on that. Now, the idea of this is actually a bigger sphere. So it's bigger than what we saw before. And not only is it bigger, but if you look at this picture, it's like it has a sphere within a sphere. And, kind of like thick spheres, like almost a racquetball or something. Sphere within a sphere, nestled in amongst one another, like Russian dolls. Now, if I could draw that, that would mean as I go out from the nucleus, I'd have a finite probability there, and then it's going to get bigger as we get further away from the nucleus. Remember, as you increase n, you increase distance. So this distance is where the electron plays. That's my little electron playground analogy, is bigger. So you can think of it as a little kid. When they're really, really little, they got to stay close to mama. As they grow up, they have more energy and they can go a little bit further away from mom. Now, this region in space here, where it hits, I'll talk about that later. Okay, so I'll come back to that. Now, if we went to the 3s, well, let's just go ahead and jump to the 5s. And again, as long as we have S, it's going to be a sphere. L gives us shape. And so this would be 5s. So that's telling us, in this case, that n is equal to 5. Since we have S, that still means L is equal to 0. But that gives us 2 of our ultimately 4 quantum numbers. And you notice here it's got a sphere within a sphere within a sphere within a sphere, with a thick ball kind of sphere. Now, this is much further out. So again, it's like the electron has more energy, it's grown up, it can get further from the nucleus. And it's going further and further away, and I'll show you some nice images of that likely in our next video. Now, let me show you some of the other ones that we have for L, some of our other shapes. So let's go to P. Now, the P orbitals look like dumbbell shapes. And don't worry about the fact that there are 3 of them right now. We'll come to that later. That gets us into our 3rd quantum number. For now, we're still focusing on L, which tells us shape, and the shape is like some sort of a dumbbell shape. And so this, since it's 2p, we would say n is equal to 2 and L is equal to 1. Now to find L, I actually write down 1, 2, 3, and I'll go S, P, D, F. Otherwise I forget. I get shifted one direction or the other. Now as we move up, again, let's take a look. We would see, let's say, 4D. So let's see 4D here. Whoops. Or 5D. Now, this is cool to me. I love these. This looks like, some sort of space houses like you'd see on the Jetsons. Now, D is a little bit unique. This, if you look in here, it resembles like a clover leaf type of a shape. Again, don't worry about the fact there are 5 of them. We'll come back to that. A clover leaf shape. So we've got 4 clover leaves, except for this weird one. but it's just unique. So this was the 5D that I selected. So that 5 in front tells me that N is equal to 5, and the fact that it's a D, that letter gives me my L value, and D means L is equal to 2. And let's take a look at our F's. They're really fun as we get up into these. So we'll do 4F, and we actually have 7 of these, interestingly enough. You're going to see a lot of very neat patterns as we finish through this, all of which are reflected on our periodic table. Frankly, I'm not even going to try to describe these. So these are just the 4Fs. There are 7 of them, and we'll get into that in a minute. It's really the shape that we're after because L tells us shape. So if this is the 4F, that means N is equal to 4 because N is given by the number in front, and F is going to mean L, and in that case, L is equal to 3. So it's 0, 1, 2, 3, S, P, D, F. So that's the order. So that is our second group of orbitals, and we will come back and clean up this topic in just a minute and go on to the final one.